Until now, I have produced 548 videos in different subjects and issues. With a few exceptions, all of them were created in the Spanish language. Starting now, periodically, I will start producing videos in English. Although English is not my first language, in my life I worked and survived in English language environments in Canada, in the United States, and even in Saudi Arabia for more than 20 years. I also wrote and published several books in the English language. Therefore, with this presentation, I will start a new cycle which will have the title Facts and Fictions. Have a good day. In this presentation, we will try to demonstrate the mineral origin of hydrocarbons, especially natural gas and oil. We will explain that hydrocarbons are of mineral origin and are formed from methane that rises from the upper mantle,
experiencing partial loss of hydrogen and oxidation.
And of course, they are not of fossil origin, as is often expressed almost as a dogmatic statement. We will start by presenting some data that will allow us to understand the conclusions later. First of all, we should remember the hydrogen is the most common element and makes up 73.9% of all matter in the universe. In second place is helium with 24%, but we must point out that helium is a noble gas and therefore does not combine spontaneously with other elements.
If we consider all the elements except hydrogen and helium, almost half of the matter is composed of oxygen,
while carbon is in fourth place,
representing
approximately 0.46% and almost a fifth of the elements that we defined before as heavier. It is not surprising that since oxygen and carbon are the most common non-light elements, their main compound, carbon dioxide, is the most abundant in some planetary atmospheres of our solar system, such as on Venus and Mars. On Venus, CO2 is 96.5% of the atmosphere, and on Mars it is 95.32%. These two planets are extremely different. On Venus, the atmospheric pressure is 93 bars, while on Mars it is 10,000 times lower. Similarly, on Venus, the average temperature of the atmosphere is about 48 degrees centigrade, while on Mars it is about 70 below zero. However, despite these huge differences, the atmospheric composition in relation to CO2 is similar. It is striking that the Earth, which is located between Venus and Mars, regarding its distance from the Sun, has only 0.04 of CO2, which means that it strangely has 2,000 times less CO2 than any of the other two planets that we mentioned before. It is very likely that the Earth originally had about the same amount of CO2 as Venus and Mars. However, now it has much less. For that reason, a question arises: where did the missing CO2 go? The answer is logical. The missing CO2 is in the limestones, which are rocks made up of carbonates and which represent about 20% of the Earth's sedimentary basins. The CO2, which was very abundant in the air and also in the seas, was used by a wide variety of organisms to make their skeletons and shells, which are generally made of carbonates. These organic carbonates were deposited on the muddy bottoms of the oceans, were buried by other deposits, and eventually consolidated into limestone rocks. These limestone formation processes depended on the evolution of life. There was a tendency for marine and aquatic carbonate-producing populations to increase both in complexity and extent, and for that reason, limestone formation was less in earlier times, say Proterozoic, a billion years ago, and greater in more recent times, for example, during the Mesozoic era, about 200 or 300 million years ago. Another issue to consider is that in the interior of the Earth, it is very likely that there are significant amounts of carbon due to the abundance in the original nebula. At the same time, we remember that hydrogen is usually abundant in many places because it is released from water and other hydrogenated compounds. From there, it follows that, given the conditions of pressure and temperature, carbon atoms can surround themselves with hydrogen atoms, forming methane. This situation is thought to occur in the Earth at a depth of 50 to 100 kilometers. The methane that is formed in depth tends to rise, but generally the rock masses do not allow its ascent. In any case, at some point, fractures may be generated, and through them, methane can undergo oxidation processes with oxides and sulfates, forming water with the hydrogen atoms and carbon dioxide when combining with carbon. As hydrogen oxidizes more quickly than carbon, the compound is enriched in carbon, and what was methane becomes ethane, and then propane, then butane, and so on, until forming heavier molecules such as gasoline and tar. This oxidation process is often fired up by certain bacteria which live in depth.
It is called
the hyperthermobacteria. As the methane and other hydrocarbons rise, these surging fluids are loaded with helium that may have formed in rocks formations that contain radioactive elements such as uranium. For this reason, in some places, natural gas contains helium that has nothing, absolutely nothing to do with the organic matter that those who support the fossil hypothesis speak of. In this ascent, both the methane and its derivative hydrocarbons can accumulate below impermeable clay layers that prevent them from continuing to rise, deposits that can be exploited through drilling. Hydrocarbons often manage to ascend very slowly through impermeable or semi-permeable layers. For example, shale, without being able to go through them completely, but remains impregnated inside them. These hydrocarbons contained in the shale can be extracted by the method of fracking or hydraulic fracturing, which fractures the rocks and makes rise the fluid contained in them. During the rise of hydrocarbons, oxidation processes are facilitated by the presence of oxygen-rich compounds, such as oxides and sulfates. After oxidation takes place, oxides are reduced. For example, hematite is reduced to magnetite, and sulfates can be converted into sulfides. Some of these sulfides are iron sulfides, such as pyrite, iron and copper sulfides, called chalcopyrite, lead sulfide, such as
galena,
and zinc sulfides, such as blende. The conclusion of Thomas Gold's approach is unexpected, that oil is not of fossil or biological origin, but nevertheless metal and mineral deposits
can result,
in fact, from biological processes. We will continue developing these subjects in future videos and presentations.